myself Nishu Bansal from CSC department AKGEC. Today we will see the next lecture series on the topic image processing KCS 062. These are the contents of the video, that is the image enhancement in the frequency domain. In the earlier video we have seen the image enhancement in the spatial domain, and we will see the frequency domain filters, that is the low pass filters. In the low pass filters we have the ideal, Butterworth and Gaussian low pass filters, and in the high pass filters we have the alternative for the low pass filters, that is the ideal, Butterworth and Gaussian high pass filters. At last we will see the homomorphic filtering. So let's start with the image enhancement in the frequency domain. Basically when we do the image enhancement in the spatial domain, we have the input image f of x comma y, as we have seen in the earlier video. So this f x comma y, it represents the intensities at each and every location of the image, that is the pixel intensity values. Now first what we will do is we will do the pre-processing. If we want to, for say, change the value of the pixels from the grayscale to a normalized scale, for say the grayscale has 0 to 255 values and we want to change it from 0 to 1 values. So then we can do the pre-processing in the spatial domain. After the pre-processing step, we need to convert it into the frequency domain. So spatial domain image has to be converted to the frequency domain image. That for that purpose we will use the Fourier transform. Then after applying the Fourier transform, this is the image in the frequency domain, capital F u comma v. This particular image is then, it is being applied with the filter function h of u comma v in the frequency domain. This particular filter, when it is applied on this image, the result is h of u comma v, f of u comma v, that is the filtered image. Now this particular filtered image, if we want to convert it back to the spatial domain, because the visibility of the image is only in the spatial domain, we just do the processing in the frequency domain. We do not see, we are not able to see, I should say, in the frequency domain. It's just for the processing purpose or to reduce the calculations, we convert the image from the spatial domain to the frequency domain. So we again apply the inverse Fourier transform. This would convert back the image from the frequency domain to the spatial domain. Now after this, if still we want to do the post processing, that is, now again I want to convert back the normalized image which we have represented from 0 to 1 back to the grayscale, that is 0 to 255. So for that purpose we will apply the post processing, and finally we get the enhanced image g of x comma y in the spatial domain. So these all are the basic steps that we do while we are doing the filtering in the frequency domain. So let's see what's a filter in the frequency domain. So filter is nothing but the technique. It's a technique with which certain frequency components can be chosen or it can be rejected. For example, when we talk about the low pass filter, it would select only the frequency components which are low frequency components, and it would attenuate or suppress the high frequency component. Let me tell you how this is done. For say this is my image in the frequency domain. So we have is the center of this particular image in the frequency domain. This is a DC component. Then the frequencies are radially distributed, that is they have a concentric circle around the center of the image in the frequency domain. So all these are the frequency components, these concentric circles are the frequency domain. So this particular filter, what it would do is, now it low pass filter, it would select low frequency component, that is, just remember that the components, the concentric circle which are near to the center, that is this particular circle, the near one, they represent the low frequency components, and as we move away from the center, those concentric circles, they would represent the high frequency component. So a low pass filter would retain the low frequency components and it would remove the beyond this higher frequency components would be removed. So this can be accomplished by applying the mask. Mask is nothing but in the previous slide this filter function what we have seen, that is h of u comma v is the mask directly on the image. So let's see the frequency domain filtering, how we use the mask basically. The greatest advantage of using the frequency domain is that we can manipulate spatial frequency components independently. These concentric circles that I have shown you, they can be manipulated or we can do the processing on them independently. Now for say I have a mask h of d. H of d is nothing but the frequency domain mask, that is a transfer function. It can be visualized as equivalent to a spatial domain mask. As we have seen the spatial domain mask, that is the Bose filter, the median filter, the various filters that we have seen. Similar to that, we have the mask in the frequency domain. Now if the value of the mask are 1, that is this h of d is equal to 1, then it represents a scenario of zero attenuation. That is, if I have a mask 1 and if I apply this particular mask over the image in the frequency domain, then what it would do is it would allow all the frequency components in the resultant image. Nothing would be removed or nothing would be attenuated in the image. If I have h of d equal to 0, that is I am applying a mask which has got the value 0, then this is a scenario in which there would be 100% attenuation of the values where all the frequency components are suppressed in the resultant image. That is, we are totally removing all the components, frequency components from the image. Now what we just need to do is we need to control this h of d, the value of h of d, and remember it takes value from 0 to 1. Now depending upon this value, the weight, that is the value of this h of d frequency domain mask, one can control the attenuation of the frequency components and indirectly the nature of the image enhancement. Now let's see the frequency domain over the spatial domain. Why we prefer working in the frequency domain and in what condition we should go for the frequency domain processing in comparison to the spatial domain processing. So frequency domain, it involves fewer computations as compared to the spatial domain. First thing, that is the number of calculations. The computational work decreases in the frequency domain in comparison to the spatial domain, because the convolution operation, we have seen the convolution operation in the spatial domain. In the spatial domain it is equivalent to multiplication, it merely gets converted into a multiplication operation in the frequency domain. So we can go for the frequency domain calculations. And secondly, for larger mask, that is when the size of the mask is very high, we should do the filtering in the frequency domain. And if we have to do work on the smaller mask up to the size of 9 cross 9, then we should go for the spatial domain filtering. So you can see that where we can apply the frequency domain or where we can use the spatial domain filtering. That is, it depends upon the mask size. If I have a very big mask, then I should go for the frequency domain. And then when we need to reduce the number of calculations, we should go for the frequency domain. So simply what we need to do in the frequency domain, if I have an image which is converted from spatial domain to the frequency domain using the Fourier transform, this is how we represent it, capital F u comma v. Simply we multiply the transfer function, that is the mask in the frequency domain, that is h of u comma v. This is applied over the given image and the result is we get a enhanced image g of u comma v in the frequency domain. Now let's see the two important filters in the frequency domain. The major category, that is a low pass filter first. So you should remember two things. One is that the high frequency content of the frequency domain image, or we can say that the result of the Fourier transform, it represents the edges or the sharp transitions in the gray value in an image. Now what is this? Let's see, this is an image for, say, this triangle is a simple object I am taking in a spatial domain. This particular boundaries of this particular triangle, this represents the edges, okay, of this object. So these edges are represented in the frequency domain using the high frequencies. Now regions of relatively uniform gray values. Now for, say, we have this particular area, the inside, the surface of the object. This is almost, for, say, if we represent an object with a brown color, then the entire object almost the relative uniform, it has the uniform gray values. So this would be represented in an image using the low frequency components in the frequency domain. So just remember these two things. It's very important that we should know what is represented by the frequency domain components. So high frequency component represents the transitions, sharp transitions, moving from one object to another object, the sudden change in the intensity values, or the edges also, it is represented by the high frequency components. And the low frequency components, they represent the almost the interior of any object. So now the idea is, so hence an image can be smooth. We use the low pass filters. Low pass means we allow the low frequency components to pass. That means we would retain the low frequency components, we will preserve them, and we will attenuate or remove the high frequency components. So images can be smooth in the frequency domain by attenuating the high frequency content of its Fourier transform. This is done using the low pass filter. For simplicity, we can consider only those filters which are real and radially symmetric. So here we have is the first of the low pass filter is the ideal low pass filter. It's a very simple filter. Ideal in the sense, simply how it would work is, for, say, this is an image, this is the center D0 in the frequency domain. I told you that radially concentric circle from the center of the image, they represents the frequency component. So for, say, this particular center, this particular frequency is D0. Now beyond D0 I want to attenuate, or we can say remove all the frequency components and before D0 I just want to keep all the frequency component. So the idea is keep the filter mask value equal to 1 for all D, that is the D which are less than or equal to D0. So this particular circle we have taken for, say, S to be the D0, that is the cutoff frequency value. Beyond this cutoff frequency value, the filter mask will be 0, and before this D0 all the filter mask value is 1. So by multiplying this particular h of d with the image f of u in the frequency domain, one can preserve all the frequencies up to D0. So this entire region would be preserved, and beyond this everything would be removed. Fine. This would give you the smooth effect, that is we can remove the noise, as we have seen that box filter or weighted average filter in the spatial domain, it removes the noise, that is it preserves the surface values and removes the outer or the sharp edges. So that can be done using the low pass filter in this frequency domain. Now how we choose the cutoff frequencies in the ideal low pass filter? The idea is this cutoff frequency R0. This is very important, that what we want to preserve and what we want to remove. It all depends upon this cutoff frequency R0. It determines the amount of frequency components that can be passed by the filter. So let's see, if we take a smaller value of R0, if I take very small value, so what would happen? More the number of image components would be eliminated by the filter. So more number of components would be removed. So in journal, the value of R0 is chosen such that most components of interest are passed, that is they are preserved through, while most of the components which are not of interest, they are eliminated. So we have to choose R0 very carefully, that we are not sacrificing our components by the choice of R0. So depends upon, now R0 would decide the enhancement quality of our image. Now let's see the high pass filter. High pass means higher frequency components would be preserved, and now we will remove the lower frequency component. I told you that high frequencies, they represents the edges and the sharp transitions. So we need to preserve those, and we need to remove the low frequency components. So what we have to do is hence image sharpening. So edges when we preserve, that means we are applying the image sharpening. So image sharpening in the frequency domain is done using the high pass filters. So here also we consider filters which are real and radially symmetric. So high pass filter passes all frequencies higher than a certain cutoff frequency D0 and remove all frequencies below that. So we can say it's just the complement of the low pass filter. That is, if I have an image, this is my center representing the DC component. These are the frequency component, concentric circle about the center. And if this is my cutoff for say D0, so all frequency components beyond D0 would be preserved. This would be preserved area, and this would be this entire thing. Below the D0, it would be removed. Okay. So the transfer function for this would be h of u comma v is equal to 0 if d of u comma v, that is any frequency component u comma v, d of u comma v is its distance, it is less than equal to d0, and it is equal to 1 if d of u comma v is greater than d0. So higher frequency components would be preserved. For the low pass filter, let's see, it's just see its complement. If here it is 0, here it is 1. Here it is 1, then this value would be 0. Both are complement of each other. Where the value of d of u comma v is equal to this m upon 2 and n upon 2. This is the center, m upon 2 comma n upon 2. M and n are the frequency component, number of frequency components in the horizontal direction, and n represents the number of frequency components in the vertical direction. So distance, this is actually the Euclidean distance. So that's why we have taken is the to the power 1 upon 2, that is under root. So d of u comma v is radial frequency. It involves square root because origin of the image is m cross n size, that is the number of frequency components, is centered in the frequency rectangle, that is center is u comma v is its value is m upon 2 comma n upon 2. In the circular mass, cutoff frequencies is radius of the circle. Now what is the problem with the ideal low pass filter? One of the most important problem that we face when we apply the ideal low pass filter is the ringing effect. It produces ringing artifacts, which is a visual effect where a series of lines of decreasing intensity lie parallel to the edges. That is, if I have this image, simple image, we are taking a rectangle, if I am applying the ideal low pass filter, I would get very sharp this lines, ringing. This is called ringing effect because it look like parallel ringing lines. So these artifacts are called the Gibbs ringing. So to avoid them, we have other two kind of low pass filter. One is a Gaussian low pass, other is a Butterworth low pass filter, that are used as they do not have a steep profile like a ideal filters. For nowadays, people go for the Gaussian low pass filter. That is a very good low pass filter. Ideal low pass filters people don't use much. They go for the Gaussian low pass filter. Now let's see just the difference of using the ideal and a Butterworth is the value of h of u comma v. So this is the equation or the value of, we can say, h of u comma v. This is equal to 1 upon 1 plus d of u comma v upon d naught. D naught we know cutoff frequency, and d of u comma v is the whether a component is to be cut or not, the component under consideration, and to the power 2n, where n is the order of the filter. And remember, here also the Butterworth filter would take value from 0 to 1, and d of u comma v is the distance from the origin that we have seen. If n increases, now we have to decide the value of n, the order. If we take a very high n value, then what would happen? The filter becomes sharper with increased ringing in the spatial domain. We will see ringing effect in the spatial domain if we take n value very high. So we take mostly n value equal to 1, that is it produces no ringing effect. And if we take 2n, then ringing is present, but it's not but imperceptible, not too much. So beyond that we avoid taking the n value, we take a smaller n value so that we could get good results. So frequency response does not have a sharp transitions as in the ideal high pass filter. This is more appropriate for image sharpening than the ideal high pass filter, since this is not introducing the ringing effect. Now the Gaussian low pass filter, I told you this is the demand, the filter which is in demand and which is being used by most of the people when they are applying the, when they are smoothing their images, that is a Gaussian low pass filter. The value of h of u comma v, the transfer function or the mask value here is e to the power minus d square u comma v upon 2 sigma square. D of u comma v, we know the distance of the frequency component from the center, where d of u comma v here is under root u square plus v square is the distance from the origin in the frequency plane. Then the parameter sigma. Sigma is nothing but the dispersal or the spread of the Gaussian curve. We know the Gaussian curve, na? This bell shaped curve is the Gaussian curve. Now this spread, this sigma, how much this particular curve is being spread, this represents the sigma. So larger the value of the sigma, greater we take the dispersal or the spread, larger the cutoff frequency and milder the frequency. Okay, that is not much filtering we will get. When d of u comma v is equal to sigma, the filter is down to 0.607 of the maximum value of 1. Now Gaussian high pass filters. The form of the Gaussian low pass filter we have seen is given by this, where d of u comma v is this, is the distance from the origin in the frequency plane. The parameter sigma, we know it represents the spread or the dispersal. Larger the value of sigma, larger would be the cutoff frequency. So here we will get more severe the filtering. Now image sharpening in the frequency domain. Simply if you know the transfer function in the low pass, h of LP, here LP represents a low pass filter u comma v. So the high pass filter would be h of HP u comma v would be 1 minus h of LP u comma v. So just we have to subtract it from 1. So transfer function of a low high pass Gaussian filter would be 1 minus this. This was your low pass filter value. So similarly the high pass Butterworth filter would be, after subtracting the low pass filter from 1, we will get this particular value. Now next category of filter is the band pass filter. Now for say I have an image in the frequency domain. This is the center DC component. Now these are the radially spread out concentric circles of the frequency. Now I want to just keep this particular area or the frequency band. I want to remove this particular area also, frequency components, plus I want to remove these components also. I want to discard all these components. Now how we can do this? We can do this using the band pass filters. Okay. So it would allow the frequency components if they fall in the range d of L minus d of H. Suppose this inner concentric circle of the band has the frequency dl and the outer band has the value d of H. So in between dl and dh I want to keep. So the transfer function of 1D band pass filter would be h of d. We know the mask value takes value 0 to 1. Na? So we will take its value 1 for if my d is within this band. D is anywhere over here, is between dl and dh, and for any other value it would be 0. So 2D value would be, it would be 1 where w is the width of the band. So d of u comma v lies between d naught minus w of 2 less than equal to d naught plus w of 2, where w is the width of the band and d naught is the cutoff frequency of the center concentric circle within the band. This particular value would be d naught. Within the band, the center value, otherwise it is 0. Okay. So this is band pass filter. Now I want to just remove this particular band and I want to keep all other frequency component. That is, we want to discard this band and keep this part also and this outer part also. In that case, we use the band reject. It would be just reverse of this. That is, here we have 1, here we have is the 0. If the frequency component lies within the band, remove them, and if all other components we want to retain. So for them we have is the value 1. So band reject is just the complement of the band pass filter. Okay. Here removing, effective in removing the periodic noise we have to remove. Then we can go for the band reject filters. Ringing effect is normally smaller in this particular case. So simply band pass filter value, if it is given by h of BP, band reject filter value would be given by h of BR, it would be 1 minus h of BP. Then other category of frequency domain filters is a notch filter. These are also used nowadays, that is useful in removing the periodic signals. For say this is an image and we have again the center and the concentric circles representing the frequency components. Now I don't want to remove the entire ring, this entire concentric circle. I just want to remove this particular frequency component, this component, this component and this particular frequency component, that is symmetrically which are opposite to each other. So such kind of noise, because periodic noise they represents symmetrically opposite to each other components, that can be removed using the notch filters. Now let's see the next topic within this, that is a homomorphic filtering. It's a very important topic. Basically, when we talk about the image f of x comma y in the spatial domain, it's a product of two components. One is the illumination and other is the reflectance. Illumination is how much the light we are able to see on a particular point on the surface. So some areas they may be having more illumination in comparison to the other areas. Reflectance is how much light is being reflected from that particular point. So the intensity f of x comma y, we know it's the intensity of that particular point. So it's a product of two things, that is the illumination and reflectance. Now illumination component, just remember this, they represents the low frequency components, okay, of the image, and reflectance component, they represents a high frequency component. And we know while working in the frequency domain, the computations reduces and we can separately apply, we can get the desired values if we are able to work on these components individually. So homomorphic filtering separates these components and applies two different transfer functions to have more control. So let's see, as we know f of x comma y, the intensity at any point x comma y is a product of L is illumination at that particular point, R is the reflectance. Now what we do is, now these two components need to be separated, but we know the problem in the Fourier transform is, if we have two components A cross B and we apply the Fourier transform, this is not equal to individual components, that is Fourier transform of A plus Fourier transform of B, fine. So this is not valid in the Fourier transform. Now, but remember this also, Fourier transform of A plus B, if I am able to convert A cross B to A plus B, this is equal to f of Fourier transform of A plus Fourier transform of B. Now how I can convert A cross B to A plus B? What we can do is, we can apply log to make multiplication as addition. So apply the log transformation to the image, this results in log of f of x comma y would be equal to log of illumination component plus log of reflectance component. Now apply the Fourier transform to this log of these two components separately, okay. Now design the filters separately for the illumination and reflectance components. The transfer function of the filters can be different for the two components because these two represent different values. So when we need to convert it back to the spatial domain, we need to take the inverse. So before that, apply the inverse Fourier transform to the filtered image, and at last again to offset the logarithmic value in step 1 we need to apply the anti-log function, fine. Thank you so much.